In this lecture, we will be introducing coordination compounds. And what coordination compounds are molecules that have a transition metal ion in the center of them, and then they have other molecules, typically molecules around that center atom, and they bond to that center atom. And so in solution, they stay together, unlike ionic compounds where you have a positively charged metal and a negatively charged nonmetal, and you put them in solution and they kind of fall apart. These stay together in solution. Okay? And the title slide shows just a generic example of one of these. Right? The center atom, which would be a transition metal in most cases, is yellow here, and the atoms or molecules that are coordinating it are in kind of this purple color. Right, and this is from 23, section 3 of the book. Okay. So coordination compounds contain at least one complex ion, right, which consists of a central metal cation, right, so that the thing in the center is a metal cation, and it's bonded to molecules or anions, which are called ligands. So if you hear that term ligands, that's what it's talking about. It's something that's bonding to a center cation, metal cation, in a coordination compound. I've heard this pronounced as ligands. I pronounce it ligands. I don't honestly know which one's correct, but I think you'd be fine with either. Right, the complex ion or coordination compound is associated with counter ions of the opposite charge. So if we look at this coordination compound at the bottom of the screen, so this would be our complex ion, where we have a positively charged metal, ammonia, 6 ammonia ligands to it. This whole thing, because of the positive charge on the chromium, has a positive charge. So this has to be associated, at least in a dry powder form, it would be associated with 3 negative charges to make it neutral. Right, so, and that's kind of what's shown here, right? If we write this out, chromium with 6 ammonia coordinating it, we draw brackets around it, and we denote the overall total charge on it. All right, and again, this behaves like a polyatomic ion in solution, meaning that it stays together in solution as a whole molecule. Right, the coordination number is the number of ligand atoms bonded directly to the center metal ion. So in the previous case of that chromium with 6 ammonia on it, that has a coordination number of 6, right? There's 6 ammonia around the chromium. Right? These coordination numbers are specific for a given metal ion in a particular oxidation state. Okay, the most common oxidation number in complex ions is 6, but 2 and 4 are seen as well. Components of a coordination compound. Right, so if we have the coordination compound cobalt with 6 ammonia around it, and draw that in brackets, so that is our complex ion, and it's associated with 3 chlorines to balance the charge. When it dissolves in water, the 6 ligands again remain bound to that complex ion. Right. Another way we can draw this, another one here is shown potassium 2 with the complex ion platinum tetrachloride. Okay, so when this dissolves in water, we have 2 potassium counter ions that are released, and then this platinum tetrachloride stays together in solution. And so those are shown in this figure, right? So in a solid, you have your complex ion and your chlorines that balance the charge. When you dissolve it in water, you get the charged complex ion in solution plus those three chlorides. So here are some different coordination numbers that we can have, right? 2, 4, and 6 are the ones that we are really most common in this class. Okay, and the geometry of a complex ion, it depends on both the coordination number and the metal ion. Okay, so a coordination number of 2, it's very simple. That's a linear shape. Some of you hopefully remembered these shapes from when we talked about molecular shapes. They're the same, right? We've seen these before. We won't go into as many shapes as we talked about with molecular shapes, though, fortunately. 4, coordination number of 4 can either be square planar or it can be tetrahedral, right? And some examples of complex ions of each of those are shown here. And then 6 makes an octahedral shape. And remember, 6 is the most common. Right. So ligands of a complex ion are molecules, or sometimes they're anions, with one or more donor atoms. And we'll talk about what that means in a second. Okay. Each donor atom donates a lone pair of electrons to the metal to form a covalent bond. Right. Ligands are classified in terms of their number of donor atoms or teeth. Okay? And that's where the term dentate comes from. So if you have a monodentate ligand, that's a single donor atom. Bidentate ligands have 2 donor atoms, and polydentate ligands have more than 2 donor atoms. Here's a table from the book that just shows some common ligands. You don't have to memorize this. You will be seeing these more and more, so hopefully they will become sort of familiar to you. Monodentate are very simple things usually, like water, ammonia, halogens like fluorine or chlorine, the cyanide ion, hydroxide, so things like that. Okay. Nitrite, or thiocyanate, they are monodentate, but there's a choice between which atom will be the donor. Okay, so those are maybe a little bit more complex because you can be the bond to the metal through the oxygen or the nitrogen here, or sulfur and nitrogen and thiocyanate. Okay, but typically monodentate are pretty simple. Bidentate are a little bit bigger, so things like ethylene diamine, where you have a two carbon molecule that has 2 amine groups on it. So these 2 amine groups can bond to a metal, right? And so you get connection points at both of these. Right? This is abbreviated. This is a very common one that we'll see, ethylene diamine, and it's abbreviated as EN. Okay, so you'll see that abbreviation quite a bit. Okay, and the oxalate ion is sort of similar, right? But now you have 2 oxygens that coordinate. These can get fairly complex, so you can get some polydentate ligands that are shown here, where you have 3 or even more connection points. So the one that's really complex is this EDTA. Okay, and EDTA has 6 connection points and they all 6 can connect to a single metal. So bidentate and polydentate ligands give rise to rings in the complex ion. So when they coordinate and form their bonds to the metal, they form what would appear to be ring structures. A complex ion containing this type of structure is called a chelate, because the ligand seems to grab the metal like claws, right? So this, if we look at here, we have the En grabbing this cobalt, and it almost appears to be like claws grabbing into that. So they're termed chelates. We mentioned EDTA. Again, EDTA has 6 spots that it can bind, and it is shown here. So, very, very complex. I would not have you draw this EDTA. Okay. But I could expect you to draw something like this with 3 EN groups coordinating a single metal. Right, so here's just a bigger view of the EN, ethylene diamine, coordinating that metal, okay? And as well EDTA. There's lots of these sort of chelating molecules, and some of them are shown here. EDTA is in the middle, but there are others. Things like this, like EDTA, is often used in the lab or industrially. I think it's even used maybe even in swimming pools and stuff like that to chelate metal ions in water. So kind of remove them from any damaging effects. And in biochemistry, we use it to remove metals from metalloproteases when we're purifying proteins to help the protein we're purifying not get broken down. There are certain proteases, which are enzymes that chew up proteins, and they use metals to do that. And the EDTA kind of pulls the metals out of them and makes them inactive. So formulas for coordination compounds. A coordination compound may consist of a complex ion with a simple anionic counterion, a complex ion with simple cationic counterions, or a complex ion with complex anion as a counterion. Okay, when writing the formula for a coordination compound, there's certain steps and rules to follow. Okay, first, the cation is written before the anion. So just like in an ionic compound, the cation goes first, and then the anion is written. Okay, so positive charge first, then negative charge. The charge of the cation is balanced by the charge of the anion. Okay, so the charges are always balanced in these compounds. Neutral ligands are written before anionic ligands, and the formula of the whole complex ion is placed in square brackets. So if you have, we've mainly seen examples of where the same ligand is bound to the metal cation, but you can have a case where you have multiple different ligands around a metal cation. So if that's the case, any neutral ligands you have are written before the negatively charged ligands. Right, the charge of the cations is balanced by the charge of the anions, as I've mentioned. So you have to make sure that this thing balances. In this case, this molecule, this complex ion, contains a complex anion. Right, so the cobalt is coordinated by 2 ammonias and 4 chlorides. Okay, and that gives an overall negative charge. So we have to balance that out with 2 positive charges from potassium. Right, if we looked at just that coordination compound, the cobalt diamine tetrachloride has an overall charge of -2. So we need those 2 potassium plus counterions. Right, and there are neutral ammonia ligands, and those again are written first before the chloride, the negatively charged chloride ligands. And we can, if we didn't, let's say we didn't know the charge of cobalt here, because cobalt can have multiple oxidation states, we could calculate that out really based on how many positively charged potassium ions are balancing with this complex ion in brackets. Okay, so We know there are two. There's no total charge written up here, so we know that this whole thing is a +2 charge, or excuse me, a -2 charge. And we know each chlorine has a -1 charge itself, each chloride. So then we can just do the math and calculate that cobalt is a +2. Right. Here's an example of a coordination compound that has a complex cation. So cobalt with 4 ammonia and 2 chlorides, and we're balancing that out with 1 chloride anion. Okay, so that means this whole complex here has a +1 charge. All right, NH3 is neutral, Cl chloride is minus, so there's 2 minuses for chloride ligands. Overall, we have a plus charge, so that means that the cobalt is in a +3 oxidation state. Okay, so let's try a practice problem. Give the coordination number and the charge of the center metal ion in the following coordination compounds. Okay, so for A, we have zinc tetrahydroxide. So that is zinc, and we have 4 things coordinating it. Right, so the coordination number, we can draw this out. We don't really know the geometry of it, right? We just know that there's 4 hydroxides on it. So the coordination number here is 4. Okay. What about the charge? Well, we know that there's 2 sodiums that are balancing it, and each of those have a +2, or excuse me, a +1, so it's a +2 overall. The OHs are going to be negatively charged. Remember, hydroxide OH is negatively charged. So we have 4 of them. So 4 OHs will give us a -4 charge, plus the charge of the metal, so the zinc, we don't know what that is. That has to add up to an overall -2 charge, because we have these 2 sodiums that are balancing it. So we know zinc OH4, the other way we can write this, has a -2 charge, because we have 2 sodiums balancing. Okay. So what that means is zinc here, when we do that little algebra, zinc has to be a +2 charge. Now let's look at B, cobalt dichloride tetraamine, and this is written backwards. There's a typo here. Those amines should be written before the chlorides, because the amine group is neutral, but it really doesn't matter. So let's look at this. There's 1 balancing chloride anion, so this whole complex NH3, 4. That whole complex has to have a +1 charge, because it's balancing with 1 chloride. Right, so then we can say, okay, the cobalt, we don't know the charge, just call that X, plus our 2 chlorides, which are -1 each, so a total of -2. That has to add up to a +1. So when we do that, cobalt has to be a +3. Okay, and the coordination number, again, we're just counting the number of ligands. So cobalt has 2 plus 4, so the coordination number here is 6. Okay, and then finally, our platinum En2, Br2. Platinum En2 has to have a +2 charge, because we have 2 Br minuses balancing it. En is actually a neutral molecule, so it doesn't have any charge. So the platinum has to be in a +2 oxidation state, because that's what is giving us the overall charge of that complex ion. The coordination of it, now this one's a little tricky, right? You might see this 2 and think, okay, the coordination number is 2, but remember, En is bidentate, so it looks something like this. So each En has 2 connection points, so our total coordination number is 4 for this. Okay, so just remember that for things like En and EDTA, where you have multiple binding spots, it's more connection points. The coordination number is the number of connection points, not just the number that you see in that formula. Okay, this is a kind of a funny experiment that was done. I include it just to kind of where we're going in this lecture about nomenclature, why it's important. I'll try not to really test you too hard on the nomenclature. I think it's something that, you know, it sucks to kind of just try to sit there and memorize it. The more you use it, the more comfortable you get with it. But this is just a kind of a funny thing that really tells you the importance of it, right? If they talk about a molecule dihydrogen monoxide, right, which is just water, H2O, and they tried to sign a petition to have it the strict control or ban on this substance, and they listed, you know, these things about it. The major component of acid rain, eventually dissolves everything it comes into contact with, is lethal if accidentally inhaled, right? But just because you call it this, you know, scientific name, people actually signed this, and 86% of people voted to ban water. So, and that's really just because of that name. If they would have called it water, no one would probably have signed that, right? Okay. So how do we name coordination compounds? Again, the cation is named before the anion. Okay, so cations always come first. Okay. Within the complex ion, so within the brackets, the ligands are named in alphabetical order when applicable. Okay. Before the metal ion. Okay. Anionic ligands drop the "ide" and add "o" after their root name. So this is where it gets a little bit more complex. So usually, you know, like a Cl we call chloride, but when we're naming these coordination compounds, it becomes, instead of chloride, it becomes chloro. So we'll see some examples of these. So don't feel too anxious yet. Okay. Numerical prefix is used to indicate the number of ligands of a particular type. So prefixes do not affect the alphabetical order of the ligand names. Okay. Ligands that include numerical prefix in the name use the prefixes bis, tris, or tetrakis. So that's to denote 2 is bis, 3 is tris, and 4 is tetrakis to indicate their number. Right, so again, something that we probably haven't really come across in this class yet. Roman numeral is used to indicate the oxidation state for the metal, okay, if it can have more than one oxidation state. So when you see a Roman numeral in parentheses, that's indicating the charge or oxidation state of the metal. If the complex ion is an anion, we drop the ending of the metal name and add ate, A-T-E. Okay, so if we look at just some neutral and anionic ligands, right? For H2O, we call that aqua, NH3, amine, CO, carbonyl, NO is nitrosyl, F minus, Cl minus, Br minus, and I minus. The halogens are fluoro, chloro, bromo, and iodo. Hydroxide anion, we call that hydroxo in coordination compounds, and cyanide anion, we call that cyano. So some of the names of the metals, and this is where it gets maybe a little bit trickier, right? If we have iron, that's ferrate, copper is cuprate, lead is plumbate, silver is argentate, gold is aruate, tin is stannate. Okay. So again, I'm not going to be testing you on these, but just be aware of them, and we'll see names like full names like this. Typically on an exam, I will give you like a full name and the formula for it, so you don't necessarily have to have all of these memorized. Okay, if you go on to work in inorganic chemistry, it's something that you will pick up. Okay. This is another list of the rules for naming for coordination compounds. So I think it's pretty similar to the one that the ones that we've gone through from the book, but it's just a different way to put it, I guess, from a different source, and they're all together on one slide. Okay. Here is a more complete table of some ligands. So anionic ligands are shown here, and remember you add O to the end of those. Okay, some neutral ligands like ethylene, ethylene diamine, that we'll see, especially ethylene diamine, that seems to be a common one in this class. Some special names like aqua for water, and I think that's really what I wanted to point out on this slide. Right, again, just some more common ligands, showing them as either monodentate, usually monodentate ligands. Okay. So here the cation is complex. If the complex is ionic, it is written within brackets. Okay, what is the oxidation state of chromium? Okay, so we're not given the formula here. We're just given this sort of description. We have 3 chlorides binding within the complex ion. So overall, the charge of the complex ion must be a +3. Right, so we have 3 chlorides balancing it. We have to have a +3 complex ion. Each of the ligands are neutral, so chromium must have that oxidation state of +3. So ligands, amine comes before aqua alphabetically. And I'm not sure why the formula isn't showing up here, but let me just write it. So here we have, just by the description, we have chromine, guessing, let me look at the actual name. So we have triamine, triaqua, so there are 3 amines, 3 waters, on that complex, and then we have 3 chlorides balancing it. And I suppose that's not how we draw it. 3 Cls. Okay. So the name we would give this is triamine triaquachromium 3 chloride. So I would hope that if I gave you this name, that you could come up with this formula. Okay. I'm not going to ask you to do the opposite. I would never ask you to give you this formula and then have to write out the full name. I think that's just, there are a little bit too many rules to memorize. But if you go on in this, that's something that you probably will just pick up. Okay, so again, we're not seeing the formula. So here we have dichlorobis ethylene diamine platinum 4 chloride. So our formula, we have a platinum, and it's in the +4 oxidation state. Dichloro means there are 2 chlorines on that, coordinating it. Bis ethylene diamine means there are 2 ethylene diamines. And we have 1, well, let's think about this. If platinum has a +4 charge, the overall charge of this complex ion has to be a +2, so we need 2 chlorines to be balancing that charge. Okay. And again, that name would be dichlorobis ethylene diamine platinum 4 chloride. Okay, so let's try some practice problems with nomenclature. Okay, the first 2, we are writing the names of these when we're given the formula. Again, not going to have you do that on an exam, but we'll go through these nonetheless. And then the second 2, you're given the full name and you have to write the formula. Okay, so what's the systematic name of this compound? So we have the cation first, and our complex ion is an anion. So we have sodium, okay, and we don't really need to denote the number of sodiums with this. We just say sodium, okay? And if you want to find the formula and know how many there are, then you do the calculation with the charges. So we have sodium, and we have 4 hydroxides, so that would be tetrahydroxo, that's an R, zinc 8. Remember, when it's the complex ion is an anion, we add an ATE at the end of the metal. So tetrahydroxo zinc 8. Now our complex ion in the next, in part B, is a cation, so it comes first. So we have, and again, this is the one that I believe is a typo on these slides. The neutral ligand should go first, I believe. And definitely when we're writing it out, it's in alphabetical order. So this becomes amine, dichloro cobalt and the counter ion is chloride. All right, but what's the oxidation state of cobalt? That's what we have to figure out. So we know that the whole complex ion has a +1 charge because we're balancing it with 1 chloride. We know we have two negative charges from the chlorine, the two chlorides that are the dichloro part of that complex ion. So -2 plus X has to equal +1. So cobalt is in the cobalt 3 oxidation state. Okay, let's try now going from name to formula. So here we have tetraamine bromochloroplatinum 4 chloride. So complex ion is a cation. We have a platinum. Tetraamine, meaning there are 4 of them. Bromochloro, so bromo is 1 bromine, chloro is 1 chloride. And then we're balancing it with chlorine. That's our counter ion. Right, we know platinum is in the +4 oxidation state, and we have -2 from the bromo and the chloro. So overall, this has a +2 charge, that complex ion, so we need 2 chlorines to balance it. Right, and then finally, this one's a little bit tricky because we have a complex cation and a complex anion. So the cation is hexaamine cobalt 3. So cobalt with 6 amine groups around it. So that is a +3 charge. And tetrachloroferrate 3. So iron with 4 chlorines around it. Okay, how many do we need to balance? We know that this complex ion has a +3 charge, the cobalt, because we're told that, and the amine groups are neutral. What charges does the anion have? The tetrachloroferrate. Well, if iron is a +3, it's in the +3 state, and we have 4 negative charges from chlorines, so we have a +3 minus 4. So overall, that's going to be a -1 charge. So we're going to need 3 of these to balance. So we just write a 3 there as a subscript. Okay. The last thing we'll talk about in this lecture are isomers. Okay, and we'll break them down into different types of isomers. Okay, and what does that term mean, isomer? Well, isomer is a chemical species having the same number and types of atoms, but different position, which leads to different properties. Okay, there's 2 types of isomers: stereoisomers and structural isomers, also known as constitutional isomers. Okay, structural or constitutional isomers are those that have differing numbers and types of bonds. Stereoisomers are maybe a little bit trickier because they have the same number and type of bonds, but differ in the spatial arrangement of those bonds. Okay. And then these can be further broken down into optical isomers or enantiomers. Those are the different spatial arrangements that give them the property of handedness, or also known as chirality. And you can think of them as non-superimposable mirror images. And then you have what are known as geometric isomers, and those are also known as diastereomers. And something like the cis-trans, I'm not sure if we talked about that yet. You talk about this more in organic chemistry, but some of you have probably heard of those terms before. Those are geometric isomers. Right. Types of structural isomers we can have: coordination isomers. So those, you have an interchange of ligands among the coordination spheres, ionization isomers, and linkage isomers. Here's an example of a structural isomers, right? Progesterone and THC are structural isomers. They have the same number of and types of atoms, but their arrangement of the bonding is different. Okay, here's what we were talking about with cis-trans, the geometric isomers. Okay, we have the same number of atoms, same types of bonds. The bonds are just arranged differently. And what we mean by cis is both bromines here in this case, if we look at a double bond here, both bromines are on the same side of these carbons. So we call that cis. And when the bromines are on opposite sides, we call that trans. Okay, so cis and trans, those will be important. You'll deal with those a lot in organic chemistry as well. Okay. Another important type of isomers are enantiomers. Okay? And what enantiomer means are non-superimposable mirror images. Okay? Enantiomers are going to be related to each other like a right hand is related to a left hand. Okay? They have identical physical properties. So if you're trying to separate enantiomers, it can be kind of difficult because you can't. They're going to have the same boiling point, melting point, that sort of thing. So it can be very hard to separate them. Okay? And this term chirality is from the Greek word for hand. So if you think about chiral or chirality, think of hand. I think that's a good way to think of enantiomers, right? If you put your left hand up and your right hand, they're mirror images to each other. But if you try to superimpose them on top of one another, right, you have to turn them both the same direction, your thumbs are going to stick different directions, right? So you can't fully superimpose them. Right, so that's a simple example, but there are, with molecules, it can be a little bit trickier, right, to draw them. Here's an example of two enantiomers, and they have the same exact atoms, bonded the same way. Their spatial arrangement is just slightly different. So if we look at what's termed minus carbone, the bond down here at the bottom of the ring is pointing out towards us, and plus carbone, the bond is going into the screen. Okay, so that's the only difference around this carbon. So this carbon is bonded to, what's not shown here are hydrogens. So it's also bonded to one hydrogen. So in this case, the hydrogen's sticking out. In this case, the hydrogen's going back. So any carbon that's bonded to 4 different things is going to be chiral. So this chiral carbon here, just changing the chirality at that carbon, you go from something that smells like spearmint to something that smells like caraway seed, okay? So that very small change can have a very big effect on how this is perceived in our body. And that's because enzymes and receptors for signals, their active sites are very specific for the molecules. Only a certain molecule in a certain shape can fit in them. And enantiomers are also referred to as optical isomers. And that's because they rotate polarized light in a specific direction. And so that's where we get the whole like left and right thing from them, is because of the direction in which they rotate plane polarized light. So if you send polarized light through an optically active sample, you see that the polarization rotates a certain degree, and that's how you can tell, is this the R or the S, the left or the right enantiomer of this compound. Right, so in this case, that's what we're showing here. We have unpolarized light going through a filter which polarizes it. if you pass it through each of these different enantiomers, you're going to get a different rotation of that light based on which enantiomer you choose. Okay, so let's now talk about structural isomers or constitutional isomers, right? Because these will come up with coordination compounds. Okay, compounds with the same overall formula but have the atoms connected differently are known as structural or constitutional isomers. Coordination isomers occur when the composition of the complex ion, but not the compound, is different. This can occur by the exchange of a ligand and a counter ion. So if one of your counter ions moves in to be a ligand and one of your ligands moves out to be a counter ion, that would be what's known as a coordination isomer. So the overall formula, you have the same number of molecules, but they're just connected differently. Okay? You can also get this just by the simple exchange of ligands. Okay. Linkage isomers occur when the composition of the complex ion is the same, but the ligand donor atom is different. So some ligands can bind to the metal through either one of two donor atoms. So if they switch which donor atom they're bonding to the metal through, that's what's known as a linkage isomer. Here's a pair of linkage isomers. And if you look at the structure here, right, we have the NO2 group is one of our ligands. And in this case, we're binding through the nitrogen atom to the metal. In this case, we're binding through the oxygen atom. So those would be known as linkage isomers. And you can see that the properties change slightly, right? They're maybe a slightly darker color in this case. But overall, it's the same formula, just connected different. So some examples of some ligands, we've seen some of these, right? Nitrite, NO2, cyanite, which is OCN, and thiocyanate, which is SCN. These are ones that have, they're monodentate, but they have two separate ligand atoms that can bond to the metal. So these can be ligands that can have linkage isomers, right? And again, just that same example using the nitro. When it's bound through the oxygen, we call that nitrito. Okay, so there's a slight nomenclature difference, either when it's bound through the nitrogen or the oxygen of that NO2 group. Stereoisomers are compounds that have the same atomic connections but different spatial arrangements. And we've talked about those a little bit already. There are two types: geometric, which again is, if you want to refer to those primarily as cis and trans, I think that's what we're going to see mostly in this class. You can also call them diastereomers. They're arranged on the same, and that's where cis and trans means they're arranged on the same side or opposite sides. You can have other geometric isomers that aren't necessarily cis and trans. Right? And then again, optical isomers, those are the non-superimposable mirror images, also known as enantiomers, and those are called optical isomers because they can rotate plane polarized light in different directions. So example of geometric isomers, the platinum complexes in particular, those with a coordination number of 4 that are in a square planar arrangement, that's where these cis and trans isomers show up the most. So in this case, we have 2 amino groups and 2 chloro groups bound to our center platinum, right? The amino groups and chloro groups can be on the same side, or they can be on opposite sides, right? So this is, if they're on the same side, we call this cis. If they're on opposite sides, that's referred to as trans, right? And one compound, this is actually an important chemotherapy drug, cisplatin. So it's actually this cis form of this. And the trans form of it has no anti-tumor effect. So that shows you just how much the arrangement of these atoms that geometrically can have an effect on the properties of the molecule. You can also have a case where you have cis and trans isomers with higher coordination numbers. So in this case, we have a coordination number of 6, 4 amino groups and only 2 chloro groups. So depending on how we arrange those chloro groups, they can either be right next to each other, which we would refer to as cis, or they can be, apart from one another on opposite ends, and that would be referred to as trans. Right, just another way of showing this. Okay, cis, the chlorines are on the same side, and trans, they are on opposite sides. Again, just another way of showing this in a molecular model. Right, and probably one that an easier way to draw a structure like this, an octahedral structure. We're just going to have a metal, generic metal, which we refer to as M, and then our ligands are A, B, and C. Okay. Here, let's try just to practice, determine if A, B, and C are either cis or trans configuration in each of the coordination compounds. So if we look at the first one, right, let's look at A. So A, we're on the same side. So those would be cis on the same side. C is also on the same side, that'd be cis. And now we have B, opposite sides of the metal, so that would be what we refer to as trans. I guess the other way you can think about it is, this might be a little bit confusing because there's a square there, but these are actually where the bonds were. If C is bonded right next to another C, right, 90 degrees apart, that would be cis. If they're 180 degrees apart, that would be trans. Okay, the second one, again, I'll just draw the bonds in there. Again, we have A bonded right next to A, so A here would be cis arrangement. B is here in cis arrangement, and now C is the 180 degrees apart, which would be trans. Okay, and then finally, this is a case where we have all cis. So all of these are 90 degrees apart from one another. So they're all in the cis arrangement. So hopefully that hopefully you can see the cis and trans arrangements in molecules like this. For some people, it might be a little bit tricky. You have to sort of see this in 3 dimensions, which can be hard. Okay. Just another way of showing this sort of a picture where you have 3 now, either in, so cis and trans, we're talking about the arrangement of 2 of the same ligands, but you can have arrangements, higher order arrangements. So if we have 3 chlorines, we can depict what sort of geometrical isomer they are in based on the relative position of all 3. So here they're in sort of a triangle, and here they're in more of a line. Okay. Not gonna expect you to kind of know these for this class, but just understand that there are higher order geometric isomers. All right, we're gonna last thing we'll look at is optical isomers. Okay, and we've looked at a little bit so far, but this is a figure from the book, and this gets a little bit trickier now because we have bidentate ligands. So we have 2 EN groups. So we have an EN group here and an EN group here. Right? And they're again coordinating at two separate spots. So they make ring structures. So if we draw the mirror image of that, that would be shown here. Right? And then if we tried to rotate one 180 degrees to superimpose on the other, the chlorines would match up when you do that, but the direction and bonding of the two EN groups would not match up. And that's kind of what's shown here in this picture, right? Chlorines would be overlapping and superimposed, but these two groups would be going in separate directions. Okay. So that's for the cis relative to chlorines. If you draw the same molecule with transchlorine, transchloro, and two EN groups, these can be, the mirror images can be superimposed. So these are not optical isomers in that trans conformation, but they are in the cis conformation. So here's some larger slides just trying to show this. This can be really hard to see, right? So you have to kind of look at the direction of these bonds, right? This is straight up and down, and this is into the page, and this is out of the page. So you have to kind of see these in 3 dimensions to be able to do this. But if we draw the mirror image, that would be here on the right. Now we rotate the one on the right 180 degrees. And if you try to superimpose them, right, if you try to move this one back over here to superimpose them, you see that the chlorines would match up, right? The chlorines are going the same direction, but now you have the top EN group is coming out of the page and up, and on this side it's going into the page and up. So those would not superimpose on each other. Right, and this is just another way of seeing that. Okay. So here's a summary of the different types of isomers in coordination compounds. Right, we have constitutional or structural isomers and stereoisomers. Okay, so constitutional isomers, what you'll have are coordination isomers and linkage isomers. For stereoisomers, you have geometric cis-trans isomers, also known as diastereomers, or you have enantiomers, which are optical isomers. So there are four types of isomers to know. All right, so that does it for this lecture. Next time we will be talking about some coordination compound theory, in particular crystal field theory.